Next, we're going to look at the eye as an optical instrument and exactly what's going on with the optics of the eye and how we get an image. So the eye is focused by a combination of our cornea and the lens. And the lens can change shape based by using the muscles around, called the ciliary muscles, and the zonular fibers are also involved in that process. And as we stretch and pull this lens, we're able to change its shape. So for your relaxed lens, then we have this shape and then what's called accommodation. So the lens is there for the last bit of focus as we're trying to focus on things that are very different distances from our eyeball. So when we're focusing on a distant object, those muscles are relaxed, the zonulars tighten, and causes the lens to flatten, increasing its focal length. So for an object at infinity, the focal length of the eye is equal to a fixed distance, and this is about 1.7 centimeters. Then to focus on near objects, those muscles tense up. And so this is why if you're working with near objects a lot, like reading a lot, your eyes will get tired. Your guys get tired because you're using those muscles for viewing near objects. And it's much more relaxing to view something that's very far away because those muscles are relaxed. So every eyeball then has a near point and a far point based on what you can focus at those 2 points. So ideally, you should be able to focus on something at infinity. You should be able to see basically infinitely far away, and that should project an image on your retina. So the far point is hopefully infinity. The near point gets a little bit more tricky. The near point is the closest distance for which your lens can accommodate focusing. The near point is typically about 25 centimeters away, and this changes based on your age. So if you're wearing glasses or lenses, you can take them off and figure out, hold your hand up to your face and figure out how close you can hold your hand before it starts to get a little fuzzy. And it should be about 25 centimeters. If it's shorter, then that's great. As you get older, then your lens starts to be less accommodating. It becomes more hard to focus because the lens itself becomes harder, and you can no longer focus on things that are quite as far away. So you'll see the classical older person holding the book at arm's length in order to be able to read it. And this is when you need bifocals. I got my first bifocals a couple years ago because this starts happening to you when you hit 40. So other conditions of the eye that affect the focus are hyperopia and myopia, farsightedness, and nearsightedness. So this is where farsightedness is where people can focus far away but have trouble focusing on things nearby, and nearsightedness is when you can only see near and have trouble focusing far away. To correct farsightedness, you actually want a converging lens, because that converging lens will take an object that is very far away and make a virtual image that is closer by. And you'll want to put this virtual image at this person's farthest far point to be able to see it. So that might be at 25 centimeters, which is that person's typical near point. Might not be, depending on the strength of the prescription. For nearsightedness, in axial myopia, the nearsightedness is caused by the lens being too far from the retina, and in refractive myopia, the lens cornea system is too powerful for the normal length of the eye. So it kind of depends on the person what the actual cause is. I think this one is more common, but I'm not sure. So to correct nearsightedness, we actually want a diverging lens to be placed. And so what happens then is it takes an image, an object that's at infinity, and moves it closer, and it appears to be closer than it actually is. So another conditions of the eye are presbyopia and astigmatism. Presbyopia is due to reduction in the accommodation ability. So this is what I was saying, is that the near point moves back, and this is corrected typically with bifocals or reading glasses. And astigmatism is down here, that your cornea is not a nice smooth shape, it's actually got some ripples and bumps in it, which then causes ripples and bumps in the image formed on the back of the eye. And so you can get eyeglasses that kind of mirror this same bumpiness and be able to correct and see clearly. The eyeglasses are typically not given by focal length, they're given by power. And this is only because typical focal lengths are like 0.33 meters, and we don't want to deal with decimal points, I guess. So we're going to invert that. So power is equal to 1 over 0.33 meters is equal to 3 diopters. And here you see some typical magnifications. So a diopter of 3 would give us a magnification of 1.75 and make things 75% bigger. Okay, now we're going to look at an example with Harry, who needs eyeglasses. Harry's near point is 1.5 meters. So that is the nearest he can see something. We should be able to see something at 25 centimeters. So we want to take something at 25 centimeters and move it to 1.5 meters. That means we know that P is equal to 25 centimeters because that's where we want to put something to see it. We don't want to have to hold things at 1.5 meters. That means you need to have a friend hold it. You want to actually hold something in your hand to be able to see it. So the P is 25 centimeters because that's where our actual object is going to be. And we want to move it to 1.5 meters. So that means Q is equal to negative 1.5 meters because I want that to be virtual. I want Harry to be able to look through the lenses to see it, not to necessarily form the image. Forming the real image is the actual job of the eyeball. So we'll leave the eyeball to do that, and we'll adjust the image so that the eyeball can do that work properly. So again, P is 0.25 meters plus a negative 1.5 meters because, again, that's negative because it's virtual. Then we know F is equal to 0.3 meters or 30 centimeters. Then we want to convert that to diopters. And to do that, power is equal to 1 over F is equal to 1 over 0.3 meters is equal to plus 3.3 diopters. And since Harry can't see close to him, Harry is farsighted. So if you are farsighted, you have a positive prescription, and positive 3 is fairly normal, I think. Now we're going to look at a person with the opposite condition. Here we have negative 3 diopters, and that's going to correct nearsightedness. We want to figure out what the focal length is, and then if the person views an object in infinity, where will this image be formed using this lens alone? So where is the image going to be looking through the glasses that the eye then needs to put on the retina? So power again is equal to 1 over F. So F is equal to 1 over our power in diopters. So that's 1 over negative 3.0 is equal to negative 0.33 meters or negative 33 centimeters, which is actually my prescription. And then to find where the image is, that's going to be Q. So we've solved our lens equation for that. I get 1 over negative 33 centimeters minus 1 over infinity. Right? 1 over infinity is just 0. So I get negative 1 over 33 centimeters. And that means Q is equal to negative 33 centimeters. So that's pretty near to us. That the image is then 33 centimeters behind the lens, which is pretty close. It's not too far past the typical near point. And so this person can see at least up to 33 centimeters.